There we go. Hello, everybody. This is the pre-lab talk for the specific gravity experiment. You might see this noted as the salt solutions experiment. They're the exact same thing, but I think I changed all of the names over to specific gravity. So before we really jump into this, we're going to add a new concept this week on concentration. And concentration, for what we're talking about, is the amount of something in a combination of things. So, for example, if you take salt or sugar and dissolve it in water, you can, depending on how much salt is in that mixture, you'll end up with more or less salty water. And all of those things can be figured out with an actual number that is the concentration. So there's a couple of pieces to talk about. First is the solute. It's what you add to your mixture. It's usually whatever is the smaller quantity. In this case, that would be salt. Your solvent, instead of solute, your solvent is what is doing the dissolving, what is the primary component of your solution, in this case, water. Water is known as the universal solvent, so it will almost always be the solvent we're looking at. And then the whole mixture, once it's put together, is called a solution. So solute is what's dissolved, solvent is what dissolves the solute, and the solution is the whole thing. So we can look at some different measurements of those. For example, the molarity of that solution is the moles of solute per liter of solution. So if we knew the moles of salt we added, the liters of total solution we made, we could find the molarity. Molality sounds similar but slightly different, is also moles of solute, but in this case, it's divided by kilograms of solvent. So different unit, different piece. Molarity is the most common concentration unit. It's the one we will be using throughout this course, but you might see a lot of these other ones. There's the weight by volume percent. That is the weight of a substance in grams divided by the volume of total solution in milliliters, times 100 to make it an actual percent. But that does specifically need to be in grams per milliliter specifically. In this case, it's not a density, but the units look similar. There's the weight percent, which is the mass of your substance or your solute divided by your total mass times 100. And your volume percent, which is the volume of your solute divided by the volume of your total solution. This is primarily used for liquid-liquid mixtures. If you're combining two liquids together to make a solution, because it's easier to measure out the volume of a liquid than it is the volume of a solid. Two other ones you might run into are ppm and ppb. They are the amount of solute per million or per billion parts of that solution. Again, the units are very, very specific. Milligrams of solute per kilogram of solution. Milligram per kilogram is very specific for ppm. That's how you get your million-fold difference. ppb, parts per billion, is micrograms per kilogram. So these are different units of concentration and how to find them. We'll be using these a lot in this. Next thing is how to make one of these solutions, going all the way back to glassware. So I don't know if I've mentioned this up to this point yet, but all of these experiments are designed in ways that they kind of organize themselves into mini units where different pieces will build on each other. And the specific gravity experiment we're doing today is kind of the culmination of one of those first units. We've looked at how to take measurements, both mass, volume, how to find density. We're going to use density and specific gravity and concentration and calibration curves to all put these pieces together in ways that will make more sense as we go through. So going back to glassware, to make a very accurate solution, which is very important for calibration curves that I'll get into later, you need to have a very accurate solution. So to make accurate solutions, we need a volumetric flask. And they can be made two different ways. You either measure out a specific amount of a specific mass of your solute and add that to your volumetric flask, fill it to the line to make your solution. This is usually your stock solution. So going back to what I was talking about, measure out a certain amount of salt, add it to your volumetric flask, add some water, make sure it dissolves, swirl it around, then fill it up to the line. And again, make sure you mix it some so that it's uniform throughout. So that's one way to make a solution. The other way to make a solution is to take some volume from a previous solution, add it to your volumetric flask, fill it with the rest of your solvent. And that usually makes a dilute solution, and you're usually making this from a stock solution. So you'll measure out your salt, add it to your flask, make your stock solution. And then you'll take some volume from that stock solution, put it in a new volumetric flask, fill it up, mix it. Now you've made a dilute solution. And you can continue doing that, either making more dilute solutions from your stock solution, or you can also do what we're going to do this week called a serial dilution, where you take your stock solution, some volume to make a dilute solution, then take some of that dilute solution into a new volumetric flask to make a second dilute solution, and you keep going until you make all of your solutions in a series. So what's a dilution? The formal definition is making a solution weaker in force. All it really is you're making the concentration go down. You're adding more of your solvent, you're diluting it, there's less of your solute in it. So stock solutions are your first solution that is made by mixing reagents from a bottle. Again, usually this is you're measuring out a mass of a solid, adding it to make your first solution. Dilute solutions are made using another solution. A lot of times this is from a stock solution, but sometimes making it multiple dilutions from one stock solution gets difficult depending on the exact volumes you need. So you might need to make a serial dilution and take stock solution to dilute solution 1, to dilute solution 2, to dilute solution 3. But again, each time you're taking from another solution. So I said density ties into this with specific gravity. Going all the way back, density is mass over volume. So that means the density of a solution is directly related to the amount of solid solute dissolved in that solution. Again, with salt water, if you add 1 gram of salt versus 10 grams of salt versus 100 grams of salt, as your mass goes up, your density will go up as long as your volume isn't changing. And that means it tastes saltier, your density will be higher. What we'll see is the concentration will also be higher, and all of that is related to its specific gravity as well. So what is specific gravity? Specific gravity is the ratio of the density of a substance compared to the density of a standard. So if we're talking about liquid solutions, we usually compare to water. If we're looking at the density of a gaseous mixture, we usually compare that to air, earth, atmospheric air. Specific gravity does not have units. So if we jump down to the equation for a minute, density of our compound would be in grams per milliliter. Density of water is in grams per milliliter. So those units cancel out. So our specific gravity has no units. This is one of the few times that you'll have a number without a unit, but it is one of the specific times that that is intended. So specific gravity won't have any units. So as a quick example, if we have a substance with a specific gravity of 1.045, no units, what's its density? Assume the density of water is 1.000 grams per milliliter. So specific gravity, we can just plug into this equation. We can also rearrange it. What we want to find is the density of our compound, substance X. So if we multiply density of water on both sides, we'll get density of X equals specific gravity of X times the density of water. We can plug everything in and solve. So 2 things, let's check our units. We have no units times grams per milliliter, so nothing cancels out. The grams per milliliter just stays, so our units left over is grams per milliliter, which makes sense because we're looking at the density of X, and density should be in grams per milliliter. Next thing to check is our significant figures. We're doing multiplication, so we care about the number of significant figures. Our first number has 1.045. 4 significant figures. That 0 does count. It is a sandwich 0. The second number is 1.000, also has 4 significant figures. Those 3 zeros are trailing zeros with a decimal point, so all of them count as well. So both of them have 4 significant figures. Our answer should have 4 significant figures, and in this case it does. We don't need to round. So that's how to find density using specific gravity. Now what we're going to do with that is make a calibration curve. But how do we measure specific gravity? Because we talked about measuring density, so why not just do it that way? Well, you can, but to introduce another piece of equipment and specific gravity, you can use what's called a hydrometer. And if you look at the little video down at the bottom, it'll show you exactly how to measure with it, what it looks like, how to read it. But basically what happens is you put the hydrometer in a solution, and it will float or sink a certain amount based on the density of that solution. So the more dense your solution is, the more stuff there is to hold your hydrometer up, so it will float higher. The less dense your solution is, there's less to hold it up, so it will sink further down and give you a lower density reading. The lower that specific gravity is, the lower the overall density as well. So reading a hydrometer can usually be a little weird, mainly because it can be read to 3 or 4 decimal places usually. So some of the increments are written differently. This is one of the first pieces of equipment that's written in reverse. So you have lower increments up at the top, higher increments down at the bottom. And again, it goes to 3 or 4 decimal places sometimes. So some of the increments they choose look a little strange, but it's read the exact same way. You'll figure out what increment your meniscus is between and estimate that next digit. So again, watch the video. It'll walk you through exactly how to measure one of these. You'll see me do it in the, actually I think Katie does it in the experiment video. Katie is one of the old instructors, and I've checked all of that stuff, so everything's still up to date and current. Don't worry that it's not me doing the actual experiment. So calibration curves, again, that's kind of the whole point of this. What a calibration curve is you use your methodology on a known set of samples. Then you do the same methodology on an unknown sample, or in this case, we'll be doing 2 samples. And you can use the calibration curve to exactly calculate what you're looking for. Sounds like exactly what we did week 1, comparing our known samples and our unknown samples to identify what the unknown was. Same idea. In this case, we'll be using the density and concentration of our solutions so that we can find the concentration of an unknown solution. Without getting super mathy, calibration curves use linear relationships that should form a nice straight line. But a line can always be made from 2 points. So you have to have at least 3 points to make a true calibration curve, though most will use 5 or more, just to be very, very accurate and precise and know what's going on. So we'll determine the unknown's concentration through what's called interpolation. We'll use a calibration curve to look between values that we know to figure out the concentration of the unknown. For example, if we were to graph all of our known concentrations and densities and it fit this range, if our unknown was way up here, we can't do interpolation anymore. It's outside of the range we measured. Now, either we have to scrap the experiment, start over, or sometimes you can just add more samples to increase your range, which is why 5 or more is used. Maybe you go up to 7 or 9 or 15 to increase that range up to where you know it will be above your unknown. And then once your unknown falls inside that range, because it's between points you know, you use interpolation. Again, extrapolation is where you look outside of that range, and calibration curves do not work well for extrapolation. So once you fit your calibration curve with a trend line, there should be PowerPoint slides up in the web courses module that walk you through step by step how to do this in Excel and how to make this trend line or line of best fit, get its equation, and do all of the calculations. And I'll show you an example here in a minute. So we can use that equation to accurately calculate the concentration of our unknown. Here's how we do that. So for example, if we look up at the top, the first thing we have are our 4 standards. We know the concentration, 1, 0.5, 0.25, 0.125 molar. We measured the specific gravity with a hydrometer. We can calculate the density using our specific gravity formula. We can do the exact same thing with our unknowns, measure their specific gravity, calculate their density using the specific gravity formula. But if we look down at the graph, that's your actual calibration curve. The blue dots are our known samples where we know the concentration, we know the density, and we plot those. And then we create a trend line, which is the dashed blue line connecting all of those points. That dashed line has an equation that the software will calculate for us that's shown as y equals 0.0387x plus 1.0065. I'll get into what the r squared value is in a minute. Those black X's are what density falls on our trend line, and those densities are the densities of unknown 1 and unknown 2. So we can already kind of see around where their concentrations should be, and because they're between known points that we have between blue dots, we are doing interpolation to determine their concentration. So this r squared value, it is a measure of how well your line fits your data, or basically how much your data deviates from that perfect line. For a linear trend line, what we'll be using, the closer that value is to 1, the more linear the data is. If it was 1 exactly, it is perfectly linear. So what we can see from ours, an r squared of 0.9994 isn't bad. It's not exactly 1, which means it's not perfect, but that happens. Doing things in the real world, you've got random error, you've got all sorts of little errors here and there that are going to cause small deviations. But it's very, very close to 1, and so it's not big enough to worry about it being inaccurate. So this is a pretty good curve, and we can trust the numbers that we get out of it. So here's how we do the actual calculation. What we saw from the trend line equation is y equals 0.0387x plus 1.0065. That equation is written in slope-intercept form, which is y equals mx plus b. It calculates m, which is our slope, and b, which is our y-intercept for us. And so because we plot concentration on the x-axis, the x variable will always be concentration. Same thing, we plotted density on our y-axis, so y will always be density. Since we know the density of unknown 1, we can plug that in for y, solve for x, and get the concentration of our unknown. So that's what we're going to do. It's going to be y minus 1.0065 to move that over, then divide by 0.0387 to leave x by itself. Because x is by itself, and we plug in all of the numbers, the density we had from unknown 1, this is our y-intercept that was provided to us by the trend line. This is our slope provided by the trend line. We can calculate our concentration. Now again, pay attention to your significant figures. If you do, every time you change from addition and subtraction to multiplication and division, you need to check your significant figures. So if we do 1.01525 minus 1.0065, we get 0.00875. Because we're doing subtraction, we care about the number of decimal points. Our first number has 5 decimal points. Our second number has 4 decimal points. If we round 0.00875 to 4 decimal points, we lose that 5. It would be 0.0087, which would round up to 88. But again, we don't want to round since we're doing more math. Use the whole number, but make sure you write down that that 5 is no longer significant. So 0.087 is what is significant. Then we take that number divided by 0.0387 to get a really, really long number. But since we're doing multiplication and division, we care about the number of significant figures. Again, our top number was 0.00887. All of those zeros are leading, they don't count, so only the 87 counts. And remember that 5 is no longer significant, so we're down to 2 significant figures. Our bottom number has 3 significant figures, so our answer should have the lower, which is 2 significant figures, which is why it rounds to 0.23. And this is where you're really going to start to see significant figures altering your final answer. So make sure you check your significant figures. Okay. So that's how to do the calculation. You'll be doing this from the data provided that we take from the lab experiment. So if you ever need to come back and reference this slide, please feel free to. If that doesn't make sense, reach out to me. We can always work through how to do these. A couple of the other calculations you might need to do or are expected to be able to do from this is being able to use molarity to calculate either moles, molarity, or the volume you need, depending on what's given to you. So calculate the mass of sodium chloride, you'll need to make 1.00 liters of 1.000 molar solution. And this is to make the stock solution. This is the exact values that we had to use to make those solutions in lab. So molarity is moles over liters. Our solute is sodium chloride. Our solvent would be water. Our solution is the whole thing. So we know the volume, we know the molarity, we can plug those in, rearrange that to find out that the moles is 1.000 molar times 1.00 liter. The numbers I usually pick, normally I'm doing this as I'm walking around trying to explain this to you guys in lab. So I pick numbers that are really easy for me to do in my head while I'm teaching. So all of this comes out as exactly one mole, but we care about our significant figures. First number has 4 significant figures, 1.000, those are trailing zeros with a decimal point, so they count, and 1.00, so 3 significant figures, so our answer needs to have 3 significant figures. Again, it comes out exactly as 1, but to make it 3 significant figures, we need 0.00. Then we can go from mass to moles using the molar mass, and we will do an experiment later where we really explain where this number comes from, why we use it. Until that point, we will give you the molar mass. So we have our 1 mole times the 58.44 grams per mole. That is the molar mass of NaCl. Again, that would be given to you. And we do the multiplication, get 58.44 grams. Now, if we were to check our significant figures, our first number has 3, our second number has 4, so our answer should actually be rounded to 3 significant figures, 58.4 grams. So to make that solution, we would weigh out 58.4 grams, dissolve it in 1 liter of water, and we would have our 1 molar stock solution. Then we need to make a whole bunch of dilute solutions, and that's what you will see Katie do in the experiment video. She will take some volume from that solution, make a new solution out of it, and then use that solution to make another solution. And the way you do this is with a very simple formula, depending on where you see it, what textbook, what professor, what website, they all look a little bit different. But you might see C1V1 equals C2V2 or M1V1 equals M2V2. What we have written here is C stock V stock equals C dilute V dilute. And it's all the same thing. You just take your concentration times your volume equals the concentration of your new solution times the volume of your new solution. So what do we have? We need to make 100 milliliters of a 0.5 molar NaCl solution from our 1 molar starting solution. So we have our 1.0 molar starting solution. We don't know how much of that we're going to need to make 100 milliliters of a 0.5 molar solution. So we rearrange this, do all the math, and we get 50 milliliters. I'm not going to worry about significant figures for this one. It should be 2 significant figures, but writing 50 milliliters with 2 significant figures, you have to use scientific notation, and I'm not going to complicate things with that for now. Same thing, we need to make, again, 100 milliliters, this time of a 0.25 molar solution, so even more dilute, but we're making it from the 0.5 molar solution. So we do the same thing, plug in the numbers. Our starting solution is 0.5 molar. We don't know the volume of that we need for this step. We're making 100 milliliters of our 0.25 molar solution. We rearrange, and that number also comes out as 50 milliliters. This is just happenstance. We built this experiment so that all of the numbers are really easy to measure out and they fit with volumetric pipettes that we would have available in lab. It will not always be the same number for a serial dilution, but you can do the exact same math to figure out the exact volume you need. And same thing, to make 100 milliliters of a 0.125, even more dilute, solution from the 0.25, you would do the same thing and get another 50 milliliters. So what you'll see Katie do is she'll take the stock solution, take 50 milliliters from that, put it in a volumetric flask, fill it up. And that's actually what this experimental design is. And that's your 0.5 molar solution. Once you've made your solution, as long as you don't add any more NaCl or water, that concentration is constant. So you can dump that into a beaker, which is a whole lot easier to try and get more volume out of to make your next solution than out of a volumetric flask. So dump that into a beaker, take 50 milliliters from that beaker into a volumetric flask, fill it up. That's your 0.25 molar solution. Dump that, take 50 milliliters of that one to move it into the 0.1 or into another volumetric flask. Fill that up to make the 0.125 molar solution. So that's how she's going to make all of her knowns samples so that she knows the concentration of each of those. Put the hydrometer in, get the specific gravity, use the specific gravity to calculate the density, do the exact same thing with the unknowns, measure out 100 milliliters, put the hydrometer in, get the specific gravity, calculate the density. What you guys will need to do is take all of those densities and concentrations and make a calibration curve, very similar to the one over here. Again, there are slides that walk you through how to do this in Excel. If you run into issues, reach out to me. To make your calibration curve that will give you your trend line equation, make sure you show the R-squared value as well, and then you'll be able to use your trend line equation to calculate the concentration of your unknowns. And that is everything for this week, or at least for the pre-lab video. So make sure you guys watch the experiment, grab the data, look through all of that stuff, and reach out to me if you have any questions. Thanks.